Warning: the following video represents the author's point of view. Many of the postulates presented do not have scientific support, so they must be treated with reservation. The novelty of the work is to consider the influence of the isolated observer on what he observes. Although we are sometimes led to clash with the established cosmological vision, the objective is not simply to contradict the laws of physics, as they remain the same. We try, however, to answer questions such as, why do we only remember what is already in our past? Why don't we remember what's in our future? The author. Niels Bohr suggested, in 1927, that the act of measurement would influence the quantum system. That is, quantum reality would remain obscure until it was finally observed. This vision was called the Copenhagen Interpretation. The properties of light, acting now as a wave and now as a particle, would know exactly when to appear, because the operator of the system tells them what to do. Einstein did not agree with this view, saying that the particle exists, even though we are not there to see it. To expose the flaws in Bohr-Einstein's vision, Boris Podolsky and Nathan Rose designed an experiment in 1935, which became known as the EPR paradox, with the initials of the names of the three authors. Johann Baker, in his book 50 Ideas of Quantum Physics, describes the EPR experiment. Imagine a particle, perhaps an atomic nucleus, that decays to two smaller ones. According to the energy conservation rules, if a particle were not originally stationary, the two daughters should acquire opposite angular and linear momentum of equal value. The emerging particles each fly to one side, and have spins in the opposite direction. When we measure the spin direction of one particle, we instantly know the state of the other, no matter how far apart they are, or how long it could separate them. Einstein and his colleagues argued that this made no sense. Nothing could travel faster than light. Interestingly, this is the same explanation used by physicists to claim that Newton was wrong when he postulated that gravity would act instantly and at a distance. How to instantly pass a signal to a particle, which could be placed at an infinite distance? However, numerous quantum experiments, carried out over time, have shown Einstein to be wrong. The ghostly action does take place, and the particles seem to talk to each other across space and faster than light. Physicists have already tangled up the quantum properties of more than two particles, watching them change state together, tens of kilometers away. It is possible to see, in this brief explanation, the importance of the isolated observer, acting as an operator of the quantum system. According to Bohr, reality remains obscure until observed. That is, the root of the problem is in the observer, not outside of him. The videos of images of the universe are characterized by the appreciation of the role of the observer in the way he interacts with physical reality. Science does not seem to attach any importance to detail, preferring to stick to the thought that there's only what can be measured directly. To conceive importance to the observer's point of view would be to escape from this premise, entering the field of philosophy and not science. It would be a form of abstraction. However, science itself is often forced to abstract, for example, when elaborating the concepts of a future outcome of an event and a black hole. They act in the same way when they assume the existence of matter and dark energy, which, to this day, cannot be confirmed. Even the motion of a subatomic particle cannot be directly assessed, as it must first be illuminated. This unavoidably disturbs its position or speed. Any observable movement depends on being able to measure the particle's position in more than one time. Without time, Newton's laws would be useless. Dependence on the measure of time is also a characteristic of our memory, since without time particles would cease to exist, because they cannot be remembered. Instant and distance communication, also known as entanglement, weighs in favor of the ubiquity of light thesis. When it comes to our point of view, when the light emitted by a distant star spread across the Earth, it could already have been elsewhere, in infinite space. This could not be confirmed or denied, as the future has not happened yet. Newton's postulate about the instantaneous action of gravity would only be justified by our lack of direct access to future events. Without this access, the observer is forced to wait for the instantaneous manifestation of the event of gravity. In this case, it would assume the secondary nature of a restorative force, since the space could not contract if it had not stretched before. Thus, a supernova explosion could only be observed millions of years late, or when information contained in light was instantly projected onto the screen of past time. That screen is our celestial vault. Despite the immense delay, the gravity waves related to the event of the star's death would manifest instantly. This problem would be restricted to the point of view of those observing the night sky. Then, take the future light come from a star and flatten it over the two dimensions of space. This becomes possible because you could take time out of the equation in the future, since it cannot be measured directly. Without time, the circular light waves emitted by the star could not move to be superimposed on each other, allowing the formation of the future light come at the event. Note that even being imaginary, time, in this case, would be prior to the appearance of our sense of space depth, which would attribute to time the condition of being the third dimension of space, and not the fourth. The contraction of time to subliminal levels is something that should happen at the subatomic level of the universe, not the macrostructure. There is a connecting link between these two levels of matter, represented by our direct observation of events. Infinitudes become the same at all levels, because they depend on the same form of remote tracking of light. You need to live the subatomic particles, so that you can see them outside of their true position. It also needs the constant presence of light to see a distant star. That is, you see the stars after their light has already reached us. Only then could this light be traced back to our past. Even so, it is known that the past no longer exists. The Big Bang would have occurred 13.7 billion years ago. Even so, the cosmic radiation emitted by that singularity can be tracked instantly, without depending on the time and distances that separate us. Since the movement of light into our future does not exist because it cannot be measured directly, science has opted for the idea that Big Bang light, like that of stars, is coming from our past, rather than our future. It is the time in the past can be assessed, indirectly, by the limited speed of light. In order for time to contract at the subatomic level of matter, space would need to be stretched. This would result from the complementarity between time and space, predicted by the theory of relativity. If the contraction of time resulted from our inability to measure it in our future, or within the comet light of events, the expansion of the universe would be confined in that direction of the arrow of time. If the information were there on the back of cosmic radiation, it would be erased from our memory by time suppression. They could only be accessed later if there was an inversion in the direction of the arrow at time when the observer, starting to point, apparently, to his own past. When that happened, the observer would see the expansionary phase instantly and outside of its own time, or with the appearance it had in the past. This problem would be restricted to the observer's point of view, as the real arrow at time continues to point to his future. As the future doesn't exist, because it hasn't happened yet, it can be said that the observer contains time, by a principle of exclusion of access. It is there, in the direction of our past, that space arises, continually contracting. Meanwhile, time seems to stretch, also continuously, towards our event horizon.